Hi students, in this video I am going to discuss the remaining part of the chapter number 1, real numbers. There are two major topics. One is irrational numbers and the proof of irrational numbers, and the second topic is the decimal expansion of different kind of rational numbers. So let's start with the irrational number. In the lower classes we have learned that what is an irrational number. What are irrational numbers? An irrational number, a number S is called an irrational if it cannot be written in the form P by Q. For example, root 2, root 3, root 5, root 6, root 7, etc. And also pi, mathematical pi, that is also an irrational number because the decimal expansion of pi is starting from 3.14, etc. So what is the criteria you can say about the decimal expansion of irrational numbers? It non-terminating and non-terminating as well as and non-repeating. So the decimal expansion of irrational numbers satisfying these conditions we have already discussed in class 9, so I am not going to discuss in detail again. And what about root 4? Root 4 is not an irrational number. Why? Because 4 is a perfect square. Because of that root 4 we can write it as 2. So 2 is not an irrational number. Square root of all the natural numbers are irrationals except if a perfect square comes under the square root, that will not be an irrational number, that will be a rational number. Clear? What is this theorem state? Let P be a prime number. If P divides A square, then P divides A, where A is a positive integer. This theorem is actually used for proving irrational existence of irrational numbers. Very simple statement. For example, we can say if 3 divides 36, then what is 36 actually? 6 square. So we can say that if 3 divides 6 square, or in other way we can say that 6 square is divisible by 36. In both way we can, both have same meaning. Then by using this theorem we can state that then 3 divides 6 also. So if 3 divides 6 square, then 3 divides 6. Clear? So this is a very simple example we can give. Theoretical proof of this theorem is given in your textbook, but not the part of your examination syllabus, so I am not going to discuss. There are two important type of questions used to ask under the proof of irrational numbers. First type is that prove that root 5 is irrational. Root 5, root 3, root 4, root 6, root 7, like root of any natural number, that is irrational except a perfect square. Second category is that sum of irrational and irrational is irrational, given that one number is irrational. In your textbook the statement is given only like this: prove that 3 plus 2 root 5 is irrational. But in the examination question you should ask like prove that 3 plus 2 root 5 is irrational given root 5 is irrational. There are two questions, major questions. Either of this question you should ask in a very board examination. For the first category we are going to take the help of theorem 1.3. And also the method we are going to take, that one is a contradiction method. In class 9 we have discussed some proof of some theorems with the contradiction method. How first we will assume in the opposite way, in the contrary way to the given question or a given statement. Then on the solving of mathematical steps, if we get there is a contradiction, then we can say that our assumption is wrong. So obviously that given fact will be right or that will be true. Okay, so the same method we are going to. The approach of both the questions are same, but there are some differences in the steps of solving these two questions. Okay, let's see example 1 first. So that is exercise 1.3, question number 1. So for that, we have to prove root 5 is irrational. So let us assume to the contrary that root 5 is rational. Root 5 is rational. Actually, we need to prove root 5 is irrational, so we are assuming root 5 as rational. Now we are proceeding with according to our assumption. Okay? So if that is a rational, that is, we can find coprime A and B where B not equal to 0. That is very confusing because B is a denominator such that root 5 is equal to A by B. Because if it is a rational, then that can be represented as a fraction of numerator and denominator, that is A by B. Necessary condition we are taking here, A by B is a coprimes. If there are no coprimes, convert those numbers, integers, into coprime by dividing their HC. For example, if a number you have written like 4 by 6. 4 by 6, 4 and 6 are not coprimes. So, simplify these numbers by dividing their HCF of numerator and denominator. So, we will get a 4 by 2 will be 2 is the HCF. So, we will get 2 and here it will be 3. Now, they have become coprimes. So, here one more step is given in our textbook, that is R is equal to P by Q dividing by HCF. So, no need of writing that statement. We can directly say that is we can find coprime A and B such that root 5 is equal to A by B. Clear? So, we have directly consider it as A by B, as A and B are coprime. If they are not coprimes, then divide by the HCF. So, we will get that as a coprime. Clear? So, that is very simple. And once we got this statement according to our assumption, then we can modify this statement. So we can take this B to the right side, so we can modify. So what we will get here, root 5 B is equal to A. That implies root 5 B is equal to A. We modified. Then we are going to squaring on both sides. Okay, squaring on both sides. We get, what will you get after squaring? After squaring, you can see here root 5 B whole square is equal to A square. Root 5 square is 5. So 5 B square is equal to A square. Clear? So on the simplification we got this one. So what does this statement indicate? 5B square, 5 into B square is equal to A square. So therefore we can say that 5 divides A square. 5 divides A square. For example, you write 3 into 4 is equal to 12. What is the meaning of that? 3 divides 12. Similarly, 5 into B square is equal to A square. Therefore we can say that 5 divides A square. Clear? So 5 divides A square. We got it. Then by theorem 1.3, here we are going to apply the theorem 1.3. What is, if 5 divides A square, then by theorem 1.3 we can say that 5 divides A also. Because according to this theorem, if a prime number is divides square of an integer, then that is also divides that number itself. Clear? This is the first statement we are taking it as. Keep it. Now, if 5 divides A, then we can find. So we can write. A is equal to 5C. Because 5 divides A. Which means what is the meaning? 5 divided say means 5 into 2 can be 5 into 3 can be clear. So for some integer c, we can write a is equal to 5 into c. Clear. That is we modify. Substituting for a, in this equation, which is the equation we have written here, 5b square is equal to a square. Here we are going to substitute the value of a as 5c. So what we will get here? Let's see. 5b square is equal to 5c whole square. Instead of a square, we substituted as 5c. Clear. So what we will get? 5b square is equal to 25c square. 5 cancel. We will get b square is equal to 5c square. What does it indicate? B square is equal to 5c square means, therefore we can write 5 divides b square. Clear? Because b square is equal to 5 into c square, therefore 5 divides b square. Never write 5 divides divisible by b square, we don't write it. Okay, we should not write it. 5 divides b square. Then we can find that. Then by theorem 1.3, then by theorem 1.3, we can say that 5 divides b. What does it indicate? This is the second statement we got. There are two statements we have, 5 divides a and 5 divides b. So that means 5 is divides both the a and b, or both the a and b divisible by a common number 5, which means they have, both the a and b have a common factor which is 5. That contradicts the given assumption. According to our assumption, both the a and b are co-primes. Clear? So we can write, therefore a and b have at least 5 as a common factor, but this contradicts the fact a and b are co-prime. This contradiction arises due to our incorrect assumption that root 5 is rational. That means we got our assumption that root 5 is rational. That was wrong. If it was wrong, then there is only a possibility that is root 5 is irrational. So we can conclude. That root 5 is irrational. Clear? So this is the way we can solve. Now let's go to the second type of question. Prove that 3 plus 2 root 5 is irrational, given that root 5 is irrational. So this is also approaching same, assuming to the contrary way. Okay? So let's take that question. Question number 2. Let us assume to the contrary, that 3 plus 2 root 5 is rational. That is, we can find coprimes A and B. B should not be 0, okay, that is very important condition, such that if we are assuming as a rational, then we can write 3 plus 2 root 5 is equal to A by B. If it is a rational, we can write it this form. Then just to modify, because in the first question we directly taken this B to the right side because there was no operations. But now that is not possible. We have to simplify in another way. Clear? So just to simplify that, so we will get take this 3. Take this 3 to the left side. So what we will get here? 2 root 5. What we will get? 2 root 5 is equal to A by B minus 3. Clear? Simplified, we will get A minus cross multiplied or take LCM 3B divided by B. Again take this 2 to the right side. So what we will get? Root 5 is equal to A minus 3B divided by 5. When come to the right side, it will be on denominator. So, sorry, 2. It will be 2. So 2 we have taken. Clear? So now we are represented as a root 5 is equal to A minus 3B divided by 2. So on these types of question, what we have to do is that just to simplify the equation so that the given irrational term should come on the LHS and all the other integers should come on RHS. So this is we rearrange the equation. So we have to write mention here it is okay. Rearranging. The second step they have to mention, that is before they writing these steps they have to write a rearranging. Now these all are integers, as A and B are coprimes and they are integers, and 2 and 3 are also integers. So since 2, 3, A and B are integers, A minus 3B divided by 2B is rational. Why? For example, whatever the integers you are taking, 3 minus 2 into 5 divided by 7, whatever the integers you add or subtracted or what, you done the basic operations like addition, subtraction, division, you will get a rational number. Because this will, numerator will be an integer, denominator also will be an integer, whatever you have done. Clear? So because of that, the entire term will be a rational numbers. So as this condition satisfied, A, 3, B, 2, B. Okay? These all are integers. Since the entire term RHS should be a rational number. Clear? As RHS is rational, obviously LHS also should be rational. Then otherwise we cannot call that is an equation. We know that according to this, RHS is rational. So obviously LHS also rational. It should be rational because then otherwise this equalizer is not valid. So root 5 is also rational. Rational. But the problem is that already given that root 5 is irrational in the question. So but this contradicts the fact root 5 is irrational. So why this contradiction comes? Because of our incorrect assumption. So we can conclude 3 plus 2 root 5 is irrational. Yeah, because once our assumption is wrong, then we can conclude in the opposite. Okay, so this is regarding the proof of irrational numbers. Now we are moving to the next topic, decimal expansion of rational numbers. In case of rational numbers, in their decimal expansion, there are two possibilities: either terminating or non-terminating repeating. That is called recurring. When in case of irrational, we already know that neither terminate nor repeat. So let's discuss the conditions should be satisfied to get a terminating and a recurrent decimal expansion, because two categories are there. So that there will be some differences in the case of such types of rational numbers. So what is the first condition we are going to discuss? That is terminating decimal expansion. In case of terminating decimal expansion, let x equal to p by q, a rational number. The prime factorization of q, the denominator, is of the form 2 raised to n into 5 raised to n. This is the condition. The denominator should only consist of the prime factors of 2 and 5, where n and m are non-negative integers. The x has a terminating decimal expansion. Let's take some examples from your textbook so that we will get a clear idea. Exercise 1.4. Exercise 1.4. Question number 1 I am taking. Option number 2. What is that? 17 divided by 8. See, in this case of 17 divided by 8 is the denominator q, because we are written as a number x equal to p by q, where p is the denominator, q is the denominator. Okay. So here, 17 we can factorize it, 8 we can factorize it as 17 divided by 2 cube. See here, 2 cube. This 2 cube we can write it as 17 divided by 2 cube into 5 raised to 0. 5 raised to 0 is 1. So there is no power for 1. We are writing it as. The decimal expansion of 17 divided by 8 you will get it. Decimal expansion you will get a decimal expansion. You will get a 2.125. I am not going to divide it, okay? It will take time. So decimal expansion you will get a decimal expansion of 17 divided by 8 you will get it as 2.125, which means it is terminating, not continuing the decimal expansion, because of its denominator is in the form of 2 raised to m into 5 raised to n. Not necessarily always 5 is there, because we can write as 5 raised to 0. One more example I am taking from the same question, that option number 4. In case of option number 4, you can see 15 divided by 1600. See here, what is the decimal expansion, this factorization of the denominator 15 divided by. Just to find the prime factorization of the 1600, you will get it as 2 raised to 6 into 5 raised to, sorry, this seems like 26. 2 raised to 6 into 5 raised to 2. Clear? And because of that, it is decimal expansion will be terminated. Okay. And similarly, one more option I am going to take, option number 8. In case of option number 8, you can see what is 6 by 15. 6 by 15 you can write it as 6 divided by 3 into 5. It seems like not the form of 2 raised to m into 5 raised to m, but we can cancel this 3 with the numerator, so we will get 2 by 5. So by looking at a glance, you cannot decide whether it is terminating or terminating or non-terminating. If there is any common factor, simplify. After the simplification, then look at the prime factorization of the denominator. If it consists only 2 and 5, then it has terminated. And here see only 5. So we can modify this one. 2 by 2 raised to 0 into 5. So either it has 5 or 2 or 2 and 5 only. If there is any other number comes, that will not terminate. We will discuss in the second category. Clear? So these all have terminating decimal expansion because of the denominator is in the form of 2 raised to m into 5 raised to m. Let's take the second question. I'm going to discuss the second question for the same option. Actually, in the second question, it is asked that write out the decimal expansion of those rational numbers in question number 1 above which they have terminating decimal expansion. Okay, so how can we write the decimal expansion without going for long division? Okay, in case of terminating decimal expansion, in case of non-terminating, it is not possible. We have to go for the long division. Okay, so I'm going to discuss exercise 1.4, question number 2. Okay, same options I am taking here. So same options I am taking. Question number 2, option number 1. Sorry, option number 2 I am going to take. 17 divided by 8. 17 divided by denominator is 2 cube. So to write the decimal expansion without long division, just to convert the denominator into the form of exponent of 10. For that, you just multiply by 5 cube and divide it by 5 cube. So that here you will get what you will get. Numerator as well as denominator. So which is equal to 17 into what is 5 cube? 125. Divided by 2 cube into 5 cube you got. That is equal to 17 into 125 you have to multiply. On multiplication you will get this number as 125. Sorry, 2125. And 2 cube into 5 cube we can write 10 cube. Because 2 cube into 5 cube is actually 2 into 5 whole cube. That is 10 cube. That is equal to 2125 divided by 1000. What will you get? Place the decimal place towards 3 decimal places to the left. So we will get to 2.125. Without long division we can write the decimal expansion. I am going to discuss the fourth option also. In case of fourth option you can see. What is the number? 15 divided by 1600. Clear. That is equal to 15 divided by, what is the prime factorization we have written here? 2 raised to 6 into 5 square. So 2 raised to 6 into 5 square. To make into the exponent form of 10 raised to 6, we have to multiply it by 5 raised to 4. So 5 raised to 4 we can take it as, so 5 raised to 4 into 5 raised to 4. Then only 2 raised to 6, here 5 raised to 6 come. Exponent should be same of both 2 and 5. So 15 into 5 raised to 4 is actually 625 divided by, now you will get it, 2 raised to 6 into 5 raised to 6. 5 raised to 15 into 625 is equal to 9375 divided by this you can write it as 10 raised to 6, which is equal to 9375 divided by 10, 6 zeros, 4, 5, 6, which is equal to 4 decimals are there, so 4 make it here and you can write 0 0.0937.5. Very simple way we can write it. The remaining options you can try yourself. I'm going to discuss the non-terminating decimal expansion next. What is non-terminating decimal expansion? State that let P be a rational number such that prime factorization of Q is not of the form 2 raised to, that means not of the form Q not equal to 2 raised to n and 5 raised to n, then we can say that it has terminating, the decimal expansion of this number is non-terminating repeating. Let's take one example, exercise 1.4, question number 1, option number 10 I am taking here. The number is 77 divided by 210. See, 77 divided by 210. 210 we can factorize. After factorization, you will get 2 into 3 into 5 into 7. I think 1 7 we can cancel. No problem. We will get 11 divided by 2 into 3 into 5. See here, this is not the form of 2 raised to n and 5 raised to n because it consists of one more 3 in the prime factorization of denominator, even after simplification. Because of that, it never terminates. You can verify this, just divide 11 divided by, you can verify this number 2 into 3, 6, 6 into 5, 30. 11 divided by 30. The decimal expansion of this 11 divided by 30 will be 0.3666, etc. That means repeating but not terminating. So we can represent this number as 0.3 is not repeating, only the digit 6 is repeating, so we can put a bar over that number. There are different type of questions are available from this chapter, but it is in this short period of time it's not easy to discuss those questions. So try yourself, go for different types of questions, and in the next video I will discuss the chapter Irrational Numbers. So thanks for watching.